This is your presenter, Asloop Mudassar, and I am presenting slide number 1 or lecture number 1 of the course on primary physics for BS classes. This is the new course that I am starting today. The number of lectures for this course may exceed 200. In the today's lecture, I shall be discussing Coulomb's law. So here is the Coulomb law. You see that in the figure I have shown two charges Q1, Q2 separated by a distance r. Then the force between the two charges is given by Coulomb's law, which is given by equation number 1, and it is F is equal to K times Q1, Q2 over r square. Q1 and Q2 are the magnitudes of the two charges and r is the separation between the two charges. This constant K is defined as K is equal to 1 over 4 pi epsilon naught, and its value after substituting the value of epsilon naught is in terms of is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square, where epsilon naught has a value equal to 8.854 into 10 to the power minus 12 farad per meter, or in other units this is the same value but in Coulomb square, Newton inverse and meter inverse squared. That is Coulomb square over Newton meter squared. So this is the force which is called the Coulomb force, and you know that this Coulomb force is inversely proportional to the separation between the two charges provided K, which is already constant, and Q1 and Q2 are fixed, are also constant. And this epsilon naught is actually, it is a measure of how well an electric field can pass through free space. In vectorial form, I can write equation number 1 in the following form. So F12 is equal to K into Q1 Q2 over R12 squared multiplied by the unit vector R12, where the unit vector specifies the direction of the force 1-2. And this is the force exerted by Q1 on Q2. R12 is a unit vector pointing from Q1 towards Q2. So the unit vector R12 is actually a unit vector pointing in the direction of Q2 from Q1. So you may regard F12 as the force exerted by charge Q1 on charge Q2. We can also write this equation, that is equation number 3, in another form, that is F21 is equal to K into Q1 Q2 over R21 squared multiplied by unit vector R21. So R21 is a unit vector which points from the position of charge Q2 towards the position of charge Q1. So this is the force exerted by Q2 on Q1. R12 is a unit vector pointing from Q2 towards Q1. So you see that the two forces, that is the force given by equation number 3 and given by equation number 4, these two forces are equal in magnitude, but of course oppositely directed. That is, the direction of force 1-2 is opposite to that of the force 2-1. Both charges will exert force on each other. So depending upon the nature of the charges, for example, if these both charges have the same polarity, that is either both negatively charged or both positively charged, then there will be a repulsive Coulomb force between the two charges. But if there is an opposite polarity, that is, if one of the charge has opposite polarity in comparison with the other, for example, Q1 is positively charged and Q2 is negatively charged, then there will be an attractive Coulomb force between the two charges. So for the like charges, the force will be repulsive, and for the unlike charges, the force will be attractive. So it means that the Coulomb force can both be attractive and also repulsive, different from the gravitational force, which is always attractive force. And you know that the gravitational force also varies as 1 over r square. Similarly, the Coulomb force also varies as 1 over r square. And you can see that in equation number 3 and 4, in the denominator, I have r12 square and r21 square. Both these quantities are equal in magnitude because this is the square root of the distance between the two charges. Either you label it as 1 2 or you label it as 2 1. But you know that the unit vector r12 and r21 have opposite directions. So whatever you define the direction of r hat 1 2, the direction of the r hat 2 1 will be opposite. So that is what we can write this one in equation number 5 as, that is the direction of the r hat 2 1 is equal to minus r hat 1 2. Similarly, the two forces from equation number 3 and 4 can be written in the form, that is the force 2 1 is equal to minus force 1 2. You see that I have defined this notation, that the force 1 2 means that this is the force on charge 2 due to charge 1. You can define by yourself in any way, in any way you can define it. That is, you can have your own definition opposite to the definition I have given. But whatever the definition you are giving, for example, here I am giving that the force 1 2 is actually the force exerted on charge q2 by the force on charge q1. And similarly, if the force exerted by charge 2 on charge q1 will of course be opposite in direction. So equation number 5 and equation number 6 defines the sense of the forces. That is, the forces are oppositely directed, but they are equal in magnitudes. So whenever you want to determine the force between the two charges, the force is simply written by in magnitudes by equation number 1. F is equal to K into Q1 Q2 over R square. Resultant Coulomb force on charge Q1 exerted by charges Qi, where I is equal to 1, where I is equal to 2, 3, and so on up to capital N through superposition principle. Suppose that in some location there are n charges, Q1, Q2, Q3, and so on up to Qn charges, which is simply represented by Qi, where I could vary from 1 to capital N. And suppose that we want to determine the force on charge Q1 due to all the charges present there. That is, we want to determine the force on charge Q1 due to the charges Q2, Q3, Q4, and so on up to Qn. Then you know that we need to apply the superposition principle. That is, all these forces in the vectorial form can be added together to give you the resultant force, as given in equation number 17. On the left hand side, I have capital F, which is the resultant force on charge Q1. And on the right hand side, I have F12, which means that this is the force on charge 1 due to the charge 2. Similarly, plus F13 is the force on charge 1 due to charge 3. Similarly, F14 is the force on charge 1 due to charge 4, and so on. And finally, F1n mean that is, it is the force on charge Q1 due to the nth charge. And you know that we shall add these charges vectorially. Here, don't make a mistake of adding them in magnitudes, because these are basically the vector quantities. all the forces exerted by charge 2, charge 3, charge 4, and so on other charges on the charge Q1 will be vectorial quantities, will be vector quantities. And you know that when you have vector quantities, then of course their addition is given by the vector addition of vectors. So that is why, which is also known as the superposition principle. So equation number 7 gives you the resultant force on charge Q1 due to all the n charges present in the surroundings of charge Q1. Now let's discuss a simple and particular example. You see that in this figure I have three charges: Q1, which is a negatively charged, Q2 positively charged, Q3 negatively charged. And you know that the question is that I want to find the net force on charge Q1. That is how much the force is exerted on Q1 by Q2 and how much the force is exerted on Q1 by Q3. You know that Q3 is negatively charged. All the three charges Q1, Q2 and Q3 are fixed in positions. Their positions are not changing. Now Q3 is negatively charged, Q1 is also negatively charged. So Q3, the force that the charge Q3 will exert on Q1 will be in the direction of F13. That is, the Q1 charge will be repelled in the direction of the line joining Q3 and Q1. So the force Q3, the force that the charge Q3 will exert on charge Q1 will be in the direction of the force F31. So F31 may be regarded as the force. F31 mean that the force on charge 1 due to charge 3. And you know that here it will make an angle theta, for example, with the negative y direction. Now let's talk about the charge Q2. Charge Q2, which is a positively charged, and Q1 will be a negatively charged. The charge Q2 will try to attract the charge Q1 towards itself. That's why the force on the charge Q1 will have a direction F12 towards the direction of charge Q2. Because Q2 is positively charged, Q1 is negatively charged, the force on charge Q1 will be such that the charge Q2 will attract charge Q1. In the same way, the charge Q1 will also attract charge Q2. But you know that we are considering the force on charges Q1. So let's talk about only charge Q1. So on the charge Q1, the force exerted by charge Q2 will be towards charge Q2, and it is indicated by the force F12. So the force between Q1 and Q2 will be attractive force, attractive Coulomb force, which will be same in magnitude. And similarly, the force between Q3 and Q1 will be repulsive Coulomb force. Both forces, that is the force that Q1 will exert on Q3 and the force Q3 will exert on Q1 will be equal in magnitudes, but will be opposite in directions. So the force exerted by Q3 on Q1 will be shown by the direction of the force F31, which makes an angle theta with the minus y direction. And you know that the separation between Q1 and Q3 is R13 and the separation between Q1 and Q2 is R12. Now you see that I have the two vectors on Q1. One vector is along the x direction represented by F12 and the other vector is along the direction making an angle theta with the minus y direction and the force is F31. So let's see what the paragraphs says about this. Let us determine the resultant Coulomb force on charge Q1 due to Q2 and Q3. You know that there is a way of adding the vectorial vectors. Now I have two vectors F12 and F31. These are the two vector forces, And if I want to add these two vector forces, one way is to split these forces into their x and y components, and then or add all the x components of the two forces, then add all the y components of the two forces, and then construct the resultant of the two forces from the components of these forces, which will be explained as. So x components of the forces F12, its x component is equal to magnitude of the force F12, because F12 is along the x direction and the cos of 0 will be equal to 1. So F12 magnitude of F12 multiplied by cos of 0 will be the same as F12. Now I am going to determine the magnitude of the x component of the force 31. That is, what is the magnitude of F31 along the x direction. So I am representing this as, now let's calculate the x component of the force F31, which is given by the magnitude of that force and the angle between the force and the x-axis, which is a cos of 90 degree minus theta. And you know that cos of 90 degree minus theta is equal to sine of theta. And F31 mod magnitude can simply be written as F31 into sine of theta. So this is the x component. So you see that in equation number 8 and 9, I have calculated the x component of the two forces, F12 and F31. Now let's calculate the y components of the two forces. For example, F12, its y component is equal to mod of F12 multiplied by cos of 90 degree. So you see that here I am talking about the y component, and you know that the y component will make an angle of 90 degree with the, and you can see that this force F12 makes an angle of 90 degree with y-axis. You can see over here the force F12 makes an angle of 90 degree with y-axis, and then you see that mod of F12 into cos of 90 degree, because I am now going to take the projection of the force F12 on the y-axis, and the angle between the y-axis and the force F12 is 90 degree, and cos of 90 degree is 0. So that's why the y component of the force 12 in the direction of y-axis is 0. Similarly, now let's calculate the y component of the force F31. So the y component of F31 is equal to minus magnitude of a force F31 into cos of theta. Because you see that I have put this negative sign, because the projection of F31 onto the minus y-axis, I am calculating that one, and then I shall multiply that component with a negative sign so that I can calculate the component along the positive y direction. So F magnitude of F31 multiplied by the cos of theta will give you the magnitude, will give you the component in the along the minus y direction, and multiplying with this negative sign will give you a component along the positive y direction. So I have simply written in equation number 11 the y component, that is the y component of F31 is equal to minus F31 multiplied by cos of theta. So you see that using equation number 8 to equation number 11, I have substituted all these components into x components and y components. Equation number 8 and equation number 9 gives you the x component of the two forces. Equation number 10 and 11 give you the y component of the two forces. Now I shall add the x components of the two and the corresponding y components of the two to find out the result x component of the resultant force. So x component of the resultant force, I am representing it by capital R. So the x component of the resultant force will be Rx, and it will be equal to sum of the two components of the two forces, that is the x component of the force 1, 2 plus the x component of the force F31. So substituting their values from previous equations, that is from equation number 8 and equation number 9, substituting these values in these two in equations, I am getting F12 plus F31 sine of theta. Similarly, the y component of the resultant force is given by Ry is equal to the y component of the force 1, 2 plus the y component of the force 3, 1. And substituting their values from equation number 10 and 11 respectively, I get this 0 minus F31 cos of theta. Now you see that I have to find out, I have to construct the resultant force. That is, I have to construct the magnitude of the resultant force and I have to calculate the direction of the resultant force. Because you know that when there is a force, you need two quantities to specify them. One is the magnitude of the force and the other is the direction of the force. And here we shall specify the direction of the force with respect to x-axis. Because you see that I am using this x and y axis as the rectangle coordinate system, and I shall specify the direction of the forces with respect to positive x direction. Now the resultant of the two forces is given by magnitude of the resultant force is equal to capital R. The magnitude is represented by the mod of the R vector is equal to the square root of Rx square plus Ry square. And now I am putting the value of Rx square from equation number 12, and I am putting the value of Ry square from equation number 13, which I have substituted over here. Now the matter is just a simplification. You have found the resultant from equation from the first step, but if you want to rewrite the resultant in some more beautiful mathematical equation, then you need to carry out some mathematical manipulations. That is, you can expand this one, that is the square of f1 plus f31 sine theta can be expanded as f12 squared plus f31 squared into sine square theta plus 2 times of f12 f31 into sine of theta. That is a square plus b square plus 2ab. I have used this formula, and then the last term is f31 squared into cos square of theta. Now you see that I can combine f31 squared sine squared theta and f31 squared into cos square theta, because in these two terms f31 squared is common, and the terms will be sine square theta plus cos square theta, which will be equal to 1. So I have written f12 squared plus f31 squared plus 2 into f1 plus f12 and f31 into sine of theta. Now the direction of the resultant force is given by. So let me represent that direction by the angle phi. You know that in the previous diagram, that is this diagram, I have represented the direction of the force F31 by an angle theta, which it makes with the negative y-axis. Now this angle, which I am going to define phi, will be the angle that the resultant force will make with the x-axis. So this is phi, which is equal to tan inverse of Ry over Rx. You know that if you simply apply the tan of phi, that will be equal to the perpendicular divided by the base. And the perpendicular is Ry component and the base is Rx component of the resultant. So the tan of phi is equal to, which is equal to Ry over Rx, and phi will be equal to tan inverse of Ry over Rx. And this is tan inverse of, I am substituting the value of Ry in the numerator and Rx in the denominator. So the magnitude is given by equation number 14 and the direction of the resultant is given by equation number 15. Let's find out the resultant in another way. You know that the resultant force on Q1 due to Q2 and Q3 can also be written as resultant vector capital R is equal to Rx into unit vector I plus Ry into unit vector J. And I have substituted the value of Rx from the previous result and the value of the y component of the resultant also from the previous result, where I hat is a unit vector along the x direction and j hat is a unit vector along the y direction. Now you see that this method of adding the two components can also be explained through the diagram which is shown over here. That is F12 is the vector and I have shifted the vector 3, 1 in such a way that the direction and the magnitude of the vector are not changing, and I have displaced this vector in such a way that its tail, that is the vector, that is the tail of the vector f13 coincides with the head of the vector 1, 2, which you can see over here, that the two vectors shown in the black, that is the two forces shown in black, are being added by head to tail rule. And the resultant vector R is given by joining the tail of the first vector to the head of the last vector and represented by the red arrow and indicated with a vector capital R. So this vector capital R will make an angle phi with the x-axis, and the phi is what I have described in the previous equation. So you see that this vector R is actually given by equation number 16. The magnitude of the resultant is given by equation number 14. Direction is given by equation number 15. And the graphical representation is shown in the diagram. Equation number 14 gives you the magnitude of the resultant. Equation number 15 gives you the direction of the resultant. And the diagram gives you the graphical representation of the addition of the two vectors, F12 and F31. So you see that if you want to determine the resultant in the parameters of the problem, you need to represent the force F12 and the force 31 in appropriate form. And also you need to determine the value of the angle theta. So if you determine these three values, you can substitute these three values in equation number 16, and you can then would be able to determine the value of the resultant capital R shown in this diagram by the red arrow. So F12 is equal to K times Q1 Q2 over R12 squared, and F31 is equal to K into Q3 Q1 divided by R12 square. So F12 is the magnitude of the force F12, F31 is the magnitude of the force between charge 3 and 1. So I can substitute F12 and F31 in equation number 16, and then I can find the resultant. So the angle theta can be found from the previous geometry. You see that in the previous geometry, the direction of the angle theta is shown. And you can determine the value of theta very easily. That is, you can determine the value of theta from the components of this vector, that is F13. Or you can determine the slope of this line, that is a Q3 and a Q1. The slope of this line will also give you the value of the angle theta. And you know that the slope is given by y2 minus y1 over x2 minus x1. That is the tan of theta is equal to y2 minus y1 over x2 minus x1. For example, the coordinates of Q3 is y2. Sorry, the coordinate of Q3 is x2, y2, and the coordinates of the tip of the vector F31 is x1 and y1. And from these two coordinates, you can easily find out the slope, or otherwise you can you know that the slope, that the coordinates of the point Q1 are 0, 0. So the slope of this line will be y2 over x2. So tan of theta will be x2 will be equal to y2 over x2, and the slope of theta, that is theta, will be equal to tan inverse of y2 over y1. So as I earlier I said that the positions of Q1, Q2 and Q3 are fixed. Although I have not specified the position of Q1, Q2 and Q3, the position of Q1 is apparently fixed. But if I have given you the position of Q3, then of course using the coordinates of Q1 and Q2, you can simply determine the slope of the angle, that is the tan of y2 over y1, and you can simply determine the value of theta by taking the tan inverse of that. So if theta is also determined, you can put the value of theta in the arguments or in the arguments of a cos and also in the arguments of a sine in equation number 16, and you can also plug in the values of f12 and f31, and then you can find out the resultant vector given by equation number 16, and this will act as a resultant force on charge q1. So you see that I have given you this example so that you can know how to work out different problems. So this is the simple problem of three charges. But if there are more than three charges are present, then you can similarly calculate the forces in the same way I have calculated. That is, you calculate the x components of each, y components of each force, and then add up all these x components and the y components separately, then construct the result x component of the resultant force, y component of the resultant force, and then you can plug in those forces, those components of the rx and ry in equation number 16 to get the resultant force on some charge. You know that for any charge q, the charge q can be expressed as q is equal to n times e, where e is the electronic charge or the charge on the electron. Its value is e is equal to 1.602 into 10 to the power minus 19 coulomb. This is the fundamental charge, and it is assumed as the fundamental charge because a free charge that could be available in space is equal to the charge of the electron. A charge smaller than this cannot be observed in space. So this is the fundamental charge, and all the charges will be equal to integer times the fundamental charge, where n could be 0, plus minus 1, plus minus 2, and so on. So any big charge can be constructed from the fundamental charge by using the value of n as shown in equation number 17. So it means that from this equation, since n is an integer, it is obvious that the charge q on the left hand side is also quantized, because the charge on the right hand side, which is the electronic charge, is also quantized. The charge is quantized, that is, exists in discrete units. So q could be equal to plus minus e, plus minus 2e, plus minus 3e, plus minus 4e, and so on. That is, q exists in discrete units. So the charge is quantized. During this course, we shall establish that mass, energy, and angular momentum will also be observed as quantized quantities. Now let's talk about the proton. You know that proton represented by the symbol P has a positive charge on it, positive E, where E is the same as the electronic charge. So the charge on the proton is the same in magnitude as the charge on the electron, but with a positive sign. And this positive E can be represented as 2 times the charge, 2 times the plus 2 over 3E plus minus 1 over E, plus minus 1 over 3 times E, where the charges in parentheses is actually the charges on the quarks. So the proton can be considered to consist of 2 quarks with the charge 2 over 3 times E, plus these are 2 quarks with the charges 2 over 3 times E, plus 1 quark with the charge minus 1 over 3E. So the proton can be considered as two quarks, as three quarks, in which two quarks have a charge of 2 over 3 times E, and one quark has a charge minus 1 over 3 times E. These quarks have not been observed in free space through any experimentation. So these are not cannot be regarded as the fundamental charge. The fundamental charge is the same as the charge on electron. Now let's talk about the neutron. You know that there is no charge on the neutron. That's why it is called the neutral particle. So neutron has no charge or zero charge. And in terms of the charge, of course, it can be represented as 2 times, that is 2 quarks with the charge minus 1 over 3e and 1 quark with the charge plus 2 over 3e. So a neutron can be considered to consist of 2 quarks, each of charge minus 1 over 3e and 1 quark with charge of 2 over 3e. So each proton and neutron consists of three charges or 3 quarks, and their charges is what I have specified. But these charges have not been observed in free space. That's why on the basis we can say that experiments have failed to show the release of free quarks. So the free charges, so in space a free charge of plus 2 over 3e and minus 1 over 3e has not been observed. So these two charges, that is the quarks, have not been observed in free space. Now let's try to solve a simple problem. Find the number of positive charges in a coin of copper. That is, we are given a coin of copper and we have to determine number of positive charges in the copper. The mass of the copper is also given in this problem. So let's try to find out the total number of charges in copper. Q is equal to N times ZE, where capital N is the number of atoms present in the coin, capital Z is the atomic mass or atomic number, and E is the fundamental charge, that is the charge on the electron. So capital Q, so Q on the left hand side is actually the total charge on the copper coin, which I have written as N times Z times E. Where you know that N times Z will actually give you the total number multiplied by the E will give you the total electronic charge. So now let's split this problem in terms of by using Avogadro number, because Avogadro number is a quantity in which we can connect mass with the number of particles present on atomic scale. So Na is actually the number of atoms in capital M gram of the copper coin, and capital M is equal to the molar mass of copper, which is represented by the gram per mole. How many grams are present in 1 mole? That is called the molar gram of copper. And capital Na is actually the number of atoms in M gram. So first of all, determine the molar gram and then determine the molar mass. And I have a quantity which is Na over capital M. This will give you the number of atoms per gram. Now multiplying with M, which is the mass of the coin. So Na over capital M multiplied M will give the atoms in M, mass of the copper. The mass of the copper is M, small m. So Na over capital M into M will give you the mass of the will give you the number of atoms in M mass of the copper. So you see that Na over capital M multiplied by M will give you the number of atoms in the M mass of the copper. And we can represent these quantities as capital N. Because I have used capital N, over here in this equation, Q is equal to capital N into Z into E, where capital N is the total number of atoms in the copper coin. And this is what I have determined in this expression. That is capital N is equal to Na over capital M multiplied by small m. So putting these values over here, because capital M is equal to 63.5 grams per mole, M is equal to 3.11 grams for the copper coin, which is given. Z is equal to 29 is the mass of, is the atomic number of the copper metal, and Na is the Avogadro number, which is equal to 6.02 into 10 to the power 23 atoms per mole. So substituting all these values in this equation, we get the value capital N to be equal to 2.95 into 10 to the power 22 atoms. Now putting the value of capital N, which is 2.95 into 10 to the power 22 atoms, putting the value of atomic number Z, which is equal to 29, and putting the charge on the electron, you will get this quantity, that is Q, that is the total charge contained in the coin, in the copper coin, is equal to 1.37 into 10 to the power 5 Coulomb. Okay, you see that I have specified this equation so that you should be able to calculate the total charge present in any substance by the way the calculations I have presented. Okay, now let's consider electron with charge A, positron with charge plus, E plus. So these two charges are opposite, are anti-particles of each other. Electron and positron having the same mass but oppositely charged. When these two charges are combined, of course, annihilation will take place. And two gamma rays are created. These two gamma rays are directed, these are the directed gamma rays which are oppositely directed with a rest mass of 2 times me square, where me c square is the mass of each of the electron and the proton. Of the positron. That is, the mass of the electron is mec square, and the mass of the positron is also mec square. So the total mass of the positron and the electron together are equal to 2 times mec square. So you see that when the gamma rays are generated, as a result, they move, or they are oppositely directed. And the rest mass of those gamma rays will be equal to 2 times mec square. So net charge before and after is conserved. You know that on the left hand side the total charge is 0, and on the right hand side I have two gamma rays, and the charge on gamma ray being an electromagnetic radiation. So the total charge on these two gamma rays is also 0. So the net charge on both sides is 0. And we can say that the net charge before and after is conserved. So you see that this reaction will take place. New particles, gamma rays, will be generated. Both will have the same rest mass. That is, on the left hand side, the rest mass of the quantities is 2mec square, and the quantities on the right hand side also have the same rest mass, which is equal to 2mec square. However, for the case of gamma rays, these rest mass will be converted into the energy of these gamma rays. So these gamma rays will have an energy which is equal to the rest mass energy, which is equal to 2mec square. Because according to Einstein's equation, E is equal to mc square. So this mass, which is mec square multiplied by 2, which was the rest mass for these initial particles before collision, will be converted into the energy of these gamma rays. Now let's consider the reaction. Meson 0, that is, this is the meson with zero charge. No charge is present on the meson. So it is called the pi meson. The pi 0 meson has no charge on it. It can decay into two gamma rays, gamma plus gamma. So the charge on the left is 0. The charge on the right is also 0. So decay of neutral pi mesons will result into two neutral gamma rays. Again, the net charge is equal to 0 before and after is conserved. That is, the charge in this reaction is also conserved. Now let's talk about the decay of neutron. This is the neutron on the left hand side, and on the right hand side of this arrow, proton is produced plus electron is produced plus neutrino is produced. So this, you may call this as the decay equation of the neutron in terms of the proton. So neutron has a charge Q is equal to 0, proton has a charge plus E, electron has a charge minus E, neutrino has a charge Q0. So you see that again the charge on the left hand side and the charge on the right hand side is also the same. Now let's discuss this relationship again. Another equation. This is electron. This is the arrow which indicates that the electron may decay into a gamma ray plus neutrino. And this arrow has been cut, indicates that the electron cannot decay into this equation because this will violate the conservation of energy. Because on the left hand side you have the charge, on the right hand side you have the neutral particles, gamma and neutrino. Both are neutral particles. So this equation, actually this equation violates the law of conservation of charge. And this could be possible, but in much time. This will require 10 to the power 22 years of lifetime to do this process, which is almost insignificant and may be regarded as impossible. Now I have also mentioned some reactions in order to explain the conservation of charge. For example, this is 2H, that is the deuterium nucleus, plus again a deuterium nucleus. Adding them, you will get tritium nucleus plus proton. The charges are mentioned below. Deuterium nucleus plus charge plus E, deuterium nucleus plus E charge, tritium hydrogen or tritium simply plus E charge, proton plus E charge. And you can see that the charges are conserved in the reaction. Let's consider another charge. Deuterium plus deuterium gives you helium-3 plus neutron. Now the charge on deuterium plus E, charge on deuterium plus E, charge on the helium nucleus is plus 2E, charge on the neutron is 0. Again, you can see that the conservation of charge is valid. That is, the charge are quantized or conserved in this reaction also. 2H is the deuterium nucleus, 3H is the tritium nucleus, 3H is the tritium is the helium. So it is, you see that this please make a correction. This is not the tritium nucleus, but this is the helium nucleus. 3H is the helium nucleus. So you see that in the today's lecture, I have covered some basics. I have covered the Coulomb's law. I have mentioned the conservation of charge by giving some simple examples. By the decay of some particles, proton, decay of neutron, decay of other particles. For example, a combination of electron and positron decay of pi meson, decay of neutron into proton, decay of other particles also. And the charge is found to be conserved. So the conservation of charge can help us to determine the authenticity of a reaction. So this is the end of slide number 1 of the primary course in physics.